Good morning, students. I'm not going to use the same joke twice. I'm uh, I'm better than that. No, I'm not, but I'm not going to do it. Um, please turn in your books to lesson 4-2, which I am projecting as part of this video. You can see it is on page 194. Let's jump right into it. Make sure your notebooks are open. We're going to take some notes right now. Orange? No way. 4-2. Oh gosh, look at that thick pen stroke. Slope and direct. There's no way I'm going to have room to finish that. Variation. Incredible. Slope and direct variation. What's our objective today? We want to understand, or rather, let's just say the student will connect proportionality to slope. This quantity we said yesterday we can understand in several different ways. So m is the symbol we usually represent for slope. M is the symbol we usually use to represent slope. It corresponds to this formula, y1 minus y2 over x1 minus x2, which we have also called, of course, delta y over delta x, also known as rise over run. And so all of this is what we mean when we say slope. Today we want to look at a particular way that slope comes up in proportional linear functions. So you will recall, hopefully, from the previous chapter, that proportional linear functions are those that pass through the origin. So I'm going to jump right into example 1, because we can see on example 1 two proportional linear functions. How do I know that they're proportional? Everybody says they pass through the origin. Excellent. So I know these are proportional because they pass through the origin. Example 1a, we've got this coordinate plane, and we can see that we pass through 0, 0 and 1, 3. And presumably that pattern is going to continue because it's proportional to 2, 6, 3, 9, and so on. Well, how are we generating these ordered pairs? How are we getting, if we were to put these together in a table real quick, how are we getting from 1 to 3, 2 to 6, 3 to 9, and so on? I mean, you can actually see right here, they give us how that's happening. Y equals 3 times x, right? So y equals 3 times x. But where is that 3 coming from? Well, recall from the previous chapter, when we have these proportional linear functions, every ordered pair, other than the origin itself, form a proportion when we put the y coordinate over the x coordinate in a ratio. So 3 to 1, 6 to 2, 9 to 3, and so on. All of these, that's not what I wanted to do, all of these end up simplifying to the 3 over x that we see in the actual equation. Now that's not quite what the book did. The book instead related this directly to slope. So it took those two ordered pairs, 0, 0 and 1, 3, and it ended up using the slope formula on those pairs. Let's try that real quick. 0, 0, 1, 3. Which one do we want to let go first? The top? Sure. Okay, so our delta y is going to be something minus something. Delta x also something minus something. In this case, the somethings are 0 and 3. So let's do 0 minus 3 for the numerator. And then the denominators, or the denominator, would come from the coordinates 0 and 1. And so we're going to do 0 minus 1 in that denominator. 0 minus 3 is negative 3. 0 minus 1 is negative 1. And of course, that works out to 3, which again, you'll notice matches the 3 in front of that x. So when we have these proportional linear functions, everything ends up pointing the exact same direction. The ratio of y-coordinates to x-coordinates equals the constant of variation. That's what we're calling that number. You can see that over here. Constant of variation equals the slope of the line. So all of this ends up working exactly the same way for a proportional linear function. Let's take a quick look at example 1b. So again, we have several different ordered pairs. We've got the line passing through 0, 0, of course, the origin, and then also going through 1, comma, negative 2. So 0, 0, and 1, comma, negative 2. And something we said yesterday is that if we notice a line moving down as we go to the right, what are we expecting about the slope of that line? Yes, we're expecting the slope of that line to be negative. So let's find out if that's what we get here when we do our delta y over delta x, minus over minus. If I am looking at an x-coordinate of 0 and a y-coordinate of 0, I might start with those. 0 minus, what's the other y-coordinate? Negative 2. What's the other x-coordinate? 0 minus 1. Very good. 0 minus negative 2, of course, we remember, oh, those two negatives turn into plus, so that's 2. 0 minus 1 is negative 1. 2 over negative 1 is the same thing as negative 2. And so that should be the equation. Y equals, or that should appear in the equation, y equals negative 2x. If I needed to, of course, I could also just put the y-coordinates in a ratio with the x-coordinates other than for the origin. And you can see in this case that's exactly the same thing that we got. 2 over negative 1, which again is negative 2. Take a minute or so and work out check your progress number 1. All right, so if we have the equation this time, they've simply given us 1/4 x, and we're supposed to name the constant of variation. And we're also given that it passes through 0, 0, and 4, comma 1, then really we should be expecting, well, of course the constant's going to be 1 over 4, but even if we weren't expecting that, as soon as we go to delta y over delta x, it becomes pretty clear. 0 minus 1 for the numerator, 0 minus 4 for the denominator. Again, y over x, make sure you're doing that. You get negative 1 over negative 4, which of course simplifies to 1/4, and that's what we see there. All right, you can see a basic explanation of what's going on there. You probably picked up on it yourself. Because one of the points is the origin, when we do the subtraction, we just end up with the ratio of y-coordinates to x-coordinates every time. And so that is why y equals kx always describes the slope of a line passing through the origin. Graph the equations. So this is actually something we're going to need to spend time on in the next few days, not just because it's going to come up over and over again throughout Chapter 4, but because I have mostly completed grading your tests. I did that yesterday, and you would be getting them back today, but for the fact that I am not there with you. But I hope to get those back to you one way or another tomorrow instead. In any case, there were a lot of issues with the graphing on the Chapter 3 test. And so this is definitely something we need to practice. Let's jump in with example 2a. So let's say we're given the equation y equals 4x, and we want to come up with a graph. What we have typically done up to this point is we've created a table of values. And what I have told you consistently is you can pick anything you want for this table of values. We usually choose x, and we usually keep the numbers small. We usually do them in order, but you can pick anything you want. Now, I'm simply going to pick, say, -1, 0, 1, 2, 3. Nothing special about those values. If you want to pick -1.5, that's fine. If you want to start at -3, that's fine. If you want to choose pi or 10 or a billion, all of that's fine. We can let x equal whatever we want. It's a variable. Its value is going to change. But once we have selected x in this case, the equation says we're going to generate a new y coordinate by quadrupling whatever that value is. So when x is -1, y is -4. When x is 0, of course, 4 times 0 is 0. When x is 1, 4 times 1 is 4. By now, you probably see a pattern. Up 4, up 4. That is going to hold up. 2 times 4 is 8. 3 times 4 is 12. And so there's our table of values. From here, of course, we treat these like ordered pairs. We go to the coordinate plane and we graph. So nothing terribly fancy going on. And yet, like I said, did give several students difficulty on the test. And so I want to look at a different way that we can graph. And this is the way that the book goes through. So the book's method works like this. Instead of generating ordered pairs, let's recognize that, of course, if it looks like this, y equals something times x, it's always going to pass through the origin. And so let's put the point there at the origin. And then if it's y equals 4x, remember this number here in front of the x corresponds to our slope. So the slope of this line must be 4. But as we discussed yesterday, it's best to understand that as a ratio because then that lets us do rise over run. And so this line is going to rise 4 and then move to the right once. Rise 4, move to the right once. Rise 4, move to the right once. You might notice we could also go down and backwards to the left once. And as we compare that to the table, that's precisely what we already had for our ordered pairs. And so now we simply connect the dots, and that's that, right? That's the equation, or rather that's the graph of the line referred to by the equation y equals 4x. Example 2b, I think, is even nicer because the k part, the constant of variation, is already a fraction. Y equals -1/3 x. Now this time, let's say I don't want to mess with the ordered pairs at all, the table at all, because I'm enamored of this new method Mr. Raschuti just showed with the rise over run. What's a point we know this line will go through? That's right, there's no plus or minus out here, so this is going to go through the origin. It's y and its x-intercept, both the same, 0, 0. But then our rise over run thing, what's the slope here now? That's right, the ratio -1/3. Notice not -1/3 x. The slope is just the part in front of the x. And so if I think of this As a rise over run, the minus 1 tells me go down 1 and then to the right 3. Down 1 to the right 3. Notice just because it's negative, I don't go down 1 and backwards 3, because that would be like two negatives canceling each other out. If I do want to go backwards 3, I would go backwards 3 and then up 1 to continue the pattern that way. And I connect the dots, and that's that. That is the graph of the line described by the equation y equals negative 1/3 x. You have 4 check your progress problems, 2A, 2B, 2C, and 2D. Please take the next several minutes to work through each one of them, graphing them in your notebook. Go. All right, you should have completed Check Your Progress 2, at least 2 or 3 of them, if not all 4 by now. For Check Your Progress 2a, y equals 6x, you can see I represented the rise over run as 6 over 1, so that means from the origin we are going up 6 over 1, up 6 over 1, or if we prefer, down 6 backwards 1. Either way, we get a very steep line passing through the origin. Check Your Progress 2b, again, pass through the origin. This time our slope is 2/3, rise over run, 2 over 3. So I've gone up 2 over 3, up 2 over 3, down 2 backwards 3, same thing. and I get the red line there. What you should notice, how do these two lines compare? Yeah, the 2/3 x is way less steep, right? And that's something that's going to come into play on this graphing calculator lab at the bottom of page 195, the kind of thing that might end up being a quiz tomorrow. And it's also going to come up on this concept summary from page 196, the kind of thing that might be good to have in your notebooks just for, future reference. Check your progress to C, y equals negative 5x. The slope there, if we express it as a ratio, is negative 5 over 1. And so that gives us a rise over run, negative 5 over 1. That means down 5 to the right 1 from the origin. Or if we did it backwards, up 5 to the left 1. And so those are the 2 points you can see there. Again, quite steep compared to B, roughly as steep as A. And then on check your progress to D, y equals negative 3/4 x. The slope is negative 3/4, rise over run again, negative 3/4. And so from the origin, you can see I went down 3 to the right 4, or up 3 backwards 4. Either way, we get the same line. Once again, way less steep than A or C, roughly as steep as B. I wonder if there's anything B and D have in common, even though one is positive, one is negative. That would be causing those to be less steep. I wonder if there's anything A and C have in common. Although again, one is positive, one is negative. That is causing those lines to be so steep. No idea, but it's an interesting thing to explore for the future. All right, one or two more examples. Let's look at example 3 here. Suppose y varies directly as x. Strange phrase, right? But every time you see this phrase, you should immediately write down y equals kx. So again, y varies directly as x. I see that phrase, I'm immediately going to write down y equals kx. Well, what does this matter? Notice they tell us y is 28 when x is 7. In other words, I can actually supply, a particular value of y is 28, a particular value for x is 7, and that's going to help me figure out what the constant of variation is. In other words, if my input is 7, x, you'll notice, is 7, and my output is 28, what must the constant of variation be? What must I be multiplying by to make that happen? Well, we could divide here by 7 to get the k by itself, right? 7 over 7 is 1. We're making ones and zeros. And so we get that 4 is the constant of variation. At this point, you would want to take this information, back up to your equation. Based on the 28 and the 7 that we were given, it's not the case that y is any kx. Instead, we can specifically say, okay, y is 4x in this context. And so then take a look at check your progress 3b. Then we can use that to solve for anything else that we want. If we're told, hey, y is 52, we can just solve that backwards and figure out what the x had to be. To get the x by itself there, hopefully you can tell, we're supposed to divide by 4. 4's cancel, making 1. And so we get the result, x is 13, right? When y is 52, x is 13. And that was the answer to example 3b. This was example 3a. Take a moment and work out check your progress 3a and 3b in your notebook. All right, you can see my work here. I started as soon as I saw that phrase, y varies directly as x. I started by writing down y equals k times x. I substituted in y was supposed to be 6 when x was negative 18. That's the information we see right here. And I simply solved for what that meant about the constant of variation k. And I got, after dividing by negative 18, that k had to be negative 1/3. I took that information back to the equation, y equals negative 1/3 x. I can now use to figure out, well, what happens when x is whatever, when y is whatever. Since x was negative 2, I plugged that in. Negative 1/3 times negative 2 is positive 2/3, and so that's my answer. Y is 2/3 when x is negative 2. I think that's that. I think we're good there. You can take a look at example 4 on your own. Certainly, if you have questions, be sure to write those down for me and ask me about those tomorrow. Your homework. Let's do 12 through 33 multiples. No, 12 through 36 multiples of 3. So pages 198. Oh, that's not readable. Pages 198 through 199, numbers 12 through 36, multiples of 3. This will be due tomorrow. Get to work on it as soon as you can, which should be in class today. I don't believe this has been 45 or 50 minutes, so you should have some time today to start working on those. Things that are coming, I've mentioned quizzes several times. Obviously not a mid-chapter quiz, we're not far enough along for that, but make sure you're happy with the notes that are in your notebook should there be a quiz when I return tomorrow. If you have questions, write those down and be sure to let me know. This video is up on YouTube, I believe. That's probably how you're watching it now, so you can comment there if you have questions. You can email me directly. Yeah, that's it. That's all I got for you. Have a good day.